Welcome back to the Fundamentals of Adjustment series. Today we are covering in episode 2 types of adjustment problems. In the previous episode we established why we need adjustment, and we saw that when we have redundant observations, more measurements than strictly necessary, I mean by that, we need a rigorous mathematical model to extract the best estimate and quantify our uncertainty. We used a simple example of measuring a wall multiple times, but I mentioned that real engineering scenarios are far more complex. So today I wanted to show you the landscape of adjustment problems in surveying and metrology. What type of measurement do we actually adjust? What are we trying to determine? And crucially, how do all these different scenarios fit into the same mathematical framework? So to recap the episode 1, in surveying and metrology and related fields, we work with spatial measurement. So what we call observation in general. These can be distances, angles, directions, coordinates, height differences, any measurement of geometric quantities. Adjustment is the mathematical process we use when we have redundant measurements. More observation than the minimum required to determine our unknowns. Adjustment answers three critical questions. First, what are the most probable values of the quantities we are trying to determine? So in other words, what is our best estimate? Second would be how uncertain are those values? What's our confidence level in those estimates? And third, how well do our measurements agree with each other? Are there any inconsistencies or potential blunders, for example? Adjustment problems in surveying and metrology fall into three fundamental categories. I've listed them in order of importance. First, network adjustment, also known as observation adjustment or parameter estimation. This is the heart and soul of least squares. We have redundant observations and geometric quantities like angles, distances, height differences, and we want to determine the best estimates of the points coordinates or other parameters that we can foresee in our model. Second, transformation determination. Here we have points measured in two different coordinate systems, and we want to find the mathematical transformation that relates them. Think of it as a calibration or a registration problem, so connecting local measurements to a global reference frame, or measured coordinates and nominal theoretical coordinates. And finally, the third one is geometric fitting. So we have measurement of points in the space, and we want to fit geometric shape or primitive like line or plane or sphere. This is essential in quality control or reverse engineering or just creating a virtual model of anything. So all three categories use exactly the same least square mathematics. The core algorithm is identical. What changes is only the input, so the type of observation we are working with and we're trying to determine. In every case, we have observations, what we measured, unknowns, what we want to find, redundancy, more observation than minimum required. Let's start with network adjustment, the most classical and fundamental application of least squares. The concept is beautifully simple, but incredibly powerful actually. We set up measuring instrument at the multiple location and make observations between points. Because we observe more than absolute minimum required, we have created a redundancy. This redundancy is what allows us to estimate best coordinates first, assess quality, detect blunders, and compute realistic uncertainties. Look at this network diagram. You can see the stations where we set up our instruments, target points, so what we are measuring, observation, the lines connecting them, representing measurements. The key principle is we measure more than we strictly need. If I want to determine the 3D position of one unknown point, theoretically I need a minimum of 3 independent observations. But in practice, we might take 10, 20, or even more observations to that point from the different stations. Now the question is, of course, why we want to have more. So the individual measurement contain errors. We cannot know it before we will put them into adjustment, so usually after our measurement. Redundancy let us average out random errors. Redundancy in turn let us detect systematic errors and blunders. More observation mean better precision, and we can assess how well our measurements agree. This is network adjustment at its core, using redundant observation to determine the best coordinates and assess quality. Now let me show the 3 specific measurement techniques that perfectly illustrate network adjustment. Each uses different type of observation, but the adjustment principle is identical and they can be adjusted all together to give 3D coordinates of the points, basically exploiting their strengths and mitigating their cons. First technique that I want to explain is polar method. It's very prevalent. So this is a method used by a laser tracker or total station, as you see here in the photo. So basically we are measuring 2 angles, horizontal angle and vertical angle, and the distance to the given point. The horizontal angle will be an angle between the arbitrary reference direction and the direction towards the point in a horizontal plane. The vertical angle is an angle between the measurement direction defined by the target point, which we try to measure, and the vertical direction defined by the axis of rotation of the instrument. And we have also a distance between the center of rotation of the telescope and the target point. These polar observation like horizontal angle, vertical angle, and distance allows us to pass freely back and forth between polar coordinate system, which we are right now, and Cartesian coordinate system where we have x, y, z. And thanks to that, give us possibility to later adjust those data in the global adjustment model. Now let's pass to the second method. This is leveling, extremely important and extremely archaic on one hand. On the other hand, it's still in use today and very important in today's network. So in leveling, we have the instrument which is leveled horizontally, so there is no possibility to incline it in vertical direction, unlike the laser tracker or total station in the previous polar method. So here we have leveled telescope and we are able to observe backside and foresight where 2 rods, leveling rods, are positioned. Basically those are 2 rulers, and thanks to scales which are marked on them, we are able to read the specific height and calculate later delta h, which is height difference between those points. And by combining multiple stations and just shifting one rod to another, we are able to create so-called leveling traverse. Calculate the height difference between points which are far away from each other. The last observation type is global positioning system, or in more general, global navigation satellite systems. Satellites in the GPS system orbit around the Earth and transmit continuously the radio signal. That radio signal includes precise position of each satellite and precise time when the signal was transmitted. so that using the GPS receiver we can pick that signal and measure travel time, how long it took for the signal to reach you from each satellite. Since we know the speed propagation of the wave, we are able to calculate the distance to each satellite. These three methods, they are basic methods of modern surveying. This is not by any means an exhaustive list, and also explanation which I gave, they are not extensive. They are just to mention how we are measuring, not getting into details. I hope that it will be possible to explain that in the future. But I wanted to introduce those methods just to let you know what we are talking about, so that the next explanation about adjustment itself will be clearer. Finishing with GNSS, we are passing to transformation determination. Here we have the transformation, which normally includes translation and rotation, sometimes also the scale factor. And basically we can imagine that we have a set of points in the first epoch and a set of points, the same point in another epoch, which was translated and rotated, and we would like to know the parameters of that transformation. And we would like to see how those two sets are fitting one to another. So in other words, if this point set didn't change. For example, if these points are representing the corners of a cube, if after transformation that cube has exactly the same dimensions. For that, least square adjustment is very helpful. And the last use of least square adjustment can be described as a geometric fitting. So let's imagine that we measure multiple points on the wall and we know coordinates of these points, and we would like to approximate somehow that wall by fitting a plane. So by fitting that plane, we will see which points are lying close to this average plane and which points are outliers. That will give us also an idea about direction of orientation of that plane, if it's inclined, if the surface is flat or rough. In general, geometric fitting is very useful in many branches of surveying and metrology, but not only. To summarize, the three main problems that we addressed today, it's network adjustment, transformation determination, and geometric fitting. All of them share a lot of similarities in terms of adjusting them, but as I mentioned before, network adjustment is something which is the most complex, and I would like to start with that part, explaining observation model, and this will be the topic of this series that we will continue.